Welcome to the second lecture on repeated cross-sections and panel data. In lecture 1, we had a look at repeated cross-sections. That is data where we observe, for instance, one group of workers in 1 year, and then a second group of workers in another year. Then we saw how we could incorporate that type of data into our regression framework. Today we'll move on and we'll have a look at panel data. And the important difference between panel data and repeated cross-sections is that with panel data we observe the same units over time. For instance, now we can imagine a case where we observe the same workers in consecutive years. With that type of data, we'll again modify the regression model that we've worked with up until now. And specifically, we will include what we call unobserved heterogeneity. Now, what we mean by unobserved heterogeneity may not be very clear at this stage. But remember, when we work with cross-sectional data, we know that individuals or firms are different, both in observable ways, in terms of x's that we can observe, but they're also different in a lot of other ways, in unobservable ways, as captured by the error term U. Now, with panel data, when we observe the same units over time, we may actually be able to sort of model some of these unobservables, and that's what we'll do today. Specifically, we'll do that in the context of the first difference estimator, which is one of the most widely used methods when it comes to panel data. Let's start by defining panel data. So usually when we say panel data, we mean that we observe the same individuals or the same firms in at least 2 time periods. In this case, I imagine having data on n individuals in 2 periods. But to be a bit more specific, in period 1, I imagine having data on my outcome variable or my dependent variable y. So on this slide you see that y has 2 subscripts. The first subscript is I, meaning that we have different observations on y for different individuals in the first period as indicated by the second subscript, the 1. Then the remaining elements in the parenthesis on the slide is just all my regressors. So here I imagine having k regressors in period 1, and they all vary across all I units. Similarly, in the second period, I also have n observations on my dependent variable y. But as you can see on this slide, now I have y subscript I and then a 2, where 2 just tells you that we're in the second period. Besides that, I still have my k explanatory variables, but now I've just changed the time index. But let's take a step back. If you look at the last element in the second parenthesis, that variable says xi to k. So k tells you that it's the kth regressor. The second to last subscript, the 2, just tells you that this is an observation from the second period. And then the first subscript, the I, just tells you that the kth explanatory variable in period 2 varies across different individuals. So that's the way we've set up the notation. I indexes individuals and T denotes time. To sum up, we imagine having a panel data available to us with n individuals, and we observe these individuals in 2 time periods. In total, that gives us 2 times n observations in the data. Up until now, we haven't been very specific about what we mean when we say period 1 and 2. In practice, they can be very far apart. Period 1 and 2 can be decades apart. Of course, we can also think of the other extreme. Period 1 and 2 can be very close to each other. They can just be days apart. That doesn't really matter for the representation of the panel data model that we're going to look at in today's lecture. One last word on panel data is that it's also known as longitudinal data. So just make sure that you understand that here we're talking about the same concept. Now, before we look at a panel data regression model, Let's just look at a couple of multiple choice questions to make sure that we understand what we mean by panel data. Here's the first question. Statistics Denmark publishes quarterly national accounts figures for Denmark on their website. Data on gross domestic production, GDP, is available from the first quarter in 1950 to the last quarter of 2013. What type of data is this? A. Cross-sectional data. B. Panel data. C. Time series data. So you should pause the online lecture here and you should go to Absalon and submit your answer. Thank you for submitting your answer. Let's move on to the second question. And it goes as follows. The World Bank has recently carried out a household survey in Uganda. In this survey, randomly selected household members are asked to keep a detailed diary of their calorie consumption of different food items over a 2-week period. The World Bank has then processed the survey data by computing the total calories consumed in each household for every food item. What type of data is this? A. Cross-sectional data. B. Panel data. C. Time series data. As before, you should go to Absalon and submit your answer and pause the online lecture meanwhile. Good job. Let's move on to the last question. In a report by the Danish Productivity Commission, data on firms from 2000 and 2010 have been used to analyze how productivity in Denmark have changed over time. Around 90% of the firms observed in the 2000 data are also observed in the 2010 data. What type of data is this? A. Cross-sectional data. B. Panel data. Or C. Time series data. As before, please submit your answer on Absalon and pause the online lecture while you do so. Thank you. Okay, let's have a look at a simple panel data model that includes unobserved heterogeneity. In this case, we're interested in a simple regression model where the dependent variable y is a function of just one explanatory variable x. The first thing to note here is that we have two subscripts on the dependent variable. So we have y, I, t. So I indexes individuals and t denotes time. So y varies across both individuals but also time. On the right-hand side of the equation, we have our usual intercept as denoted by beta naught. Then the second element is a time dummy, which is equal to 1 for the second period and 0 for the first period. That means that in the second period, this regression model will have an intercept that's the sum of beta 0 and delta naught. Besides that, we have our one explanatory variable, x. And as is the case with the dependent variable, x has two subscripts, an I and a t, meaning that x varies across individuals and across time. In this model, a 1 unit increase in x will have a beta 1 effect on y on average. Note that this effect doesn't vary across time, so it's assumed to be constant across the two time periods. The last two elements in the model is what really defines a panel data regression model. So here we have something called AI, and then something that looks like our usual error term, UIT. AI and UIT are the two error terms in the panel data regression model, and we'll talk much more about them in just 1 second. Before that, let's just remind ourselves what the time dummy does in our model. So basically, the time dummy captures what you may describe as a macro effect, that is, an aggregate change in y across the two time periods. Now, what really separates a panel data regression model from an ordinary regression model or a regression model that uses just cross-sectional data is this error term. Here we think of a combined error term that we may call epsilon IT. and it consists of two parts. The first part is AI, and the second part is UIT. So what is this AI? Well, AI is what we call unobserved heterogeneity. It basically captures some differences across individuals that do not vary across time. And more importantly, AI is not observed. It's an unobserved fixed effect. So AI captures all these differences across individuals that doesn't change over time. That's a very important assumption. What is an example of this AI? Well, think of this example of returns to education. That is, we're interested in estimating the relationship between hourly wages and education, but we're worried about the fact that we cannot observe innate ability or unobserved ability, which will be captured in the error term U. Now we can think of unobserved ability as this AI. It's something that you're born with. It's something that doesn't necessarily change a lot over time. So that's something that you can capture by this unobserved fixed effect. Now to be a little bit more specific about the assumptions regarding AI, remember that we assume that AI is time invariant. It doesn't vary across time, it varies across individuals. Or in other words, AI is assumed to be a fixed constant that's specific to each individual. On the other hand, the second part of our combined error, epsilon, is this idiosyncratic error, the U. And we assume that UIT varies randomly across both individuals and time periods, and in that way, it just acts as the usual error term that we include in our regression models. So the only difference here is that we've included this individual fixed effect, which is now part of the combined error term. So to sum up, what really separates a panel data regression model from an ordinary regression model is this assumption regarding the error structure. So for a panel data model, we typically think of an error structure that includes these two components: an unobserved fixed effect, in this case an individual fixed effects because we're working with data on individuals, and then we have our typical idiosyncratic error term. Before we move on, let's have another multiple choice question. So in this model, where y is a function of x and we have these two components of the combined error term, we've included this dummy d2 subscript t. And that dummy is included to capture level changes in y between periods 1 and 2. Now, the attentive student will note that there's no subscript I on the time dummy. Is that because A, there's a typo in the slides, the model should include d2 subscript it, or B, the time dummy captures macro effects, as such, the I index does not matter, or C, with a balanced panel, that is, a panel data where all n individuals are observed in both periods, in that case, d2it is just equal to d2t for all individuals. Again, please pause the online lecture here and go to Epsilon to submit your answer. Okay, well done. Let's move on and talk a little bit more about the assumptions for the panel data regression model. So first of all, we maintain this assumption of having a random sample, which means that there's not going to be any correlation between ui and uj. They're sampled independently of each other. Now, the second assumption I want to highlight is this assumption regarding the combined error term. Remember, a critical assumption regarding the panel data regression model is that we think of the error term as consisting of two parts: the unobserved individual specific effect, AI, and then the idiosyncratic error term, UIT. Now, an important assumption we're going to make is something that looks or should look familiar to what you've seen for the standard regression model using cross-sectional data. So this is an assumption that looks a lot like MLR4 in chapters 2 and 3 in Wooldridge. Specifically, we're going to assume that the idiosyncratic error term, UIT, is mean independent of the one explanatory variable x in both the first and the second period. Moreover, U is assumed to be mean independent of the time dummy, and then finally this unobserved individual specific effect. In other words, that implies that we're assuming that this idiosyncratic error term U is uncorrelated with X, the observed regressor, and then AI, this unobserved individual specific effect. Now the important part comes here. Note, we haven't made any assumption regarding the relationship between the unobserved individual specific effect and X, our one regressor. So if we think AI captures something like unobserved ability and X is education, then we're actually allowing for the possibility that AI, unobserved ability, is correlated with X. On the other hand, it could also be uncorrelated. We haven't specified this correlation structure at this point. However, if we think that unobserved ability, AI, is correlated with education, X, then we know that OLS will be biased and inconsistent. Or put differently, education is an endogenous regressor. So how can we alleviate this problem? Well, up until now, we've seen that one way to handle endogeneity is to use the IV estimator. That is, we look for some instrumental variable C that's correlated with the endogenous variable while being uncorrelated with the error term. However, what you will see now is that we can also handle certain types of endogeneity simply by using panel data. Okay, let's look at this situation where we think this unobserved individual specific AI is correlated with the regressor. That is, the correlation between AI and X is different from 0. As I said before, in this case we know that OLS will be biased and inconsistent. And with only one cross-section available to us, or one data set on our computer, we know that we cannot solve this problem of endogeneity without imposing additional assumptions. That is, we need an instrument. We need a valid instrument, and it needs to be relevant for the endogenous variables. But as I also said before, now that we're in this situation where we have repeated observations on the same individuals, we actually have another possible solution. And the solution is basically to transform our regression model in a way such that we can still identify and estimate the parameter of interest. In this case, that's beta 1, the slope coefficient in front of X. So we can still identify that in the transformed model, but in the transformed model, the trick is that the unobserved heterogeneity, AI, drops out. As such, we can consistently estimate beta 1. Now there's different ways of achieving this goal, but one popular method is the first difference estimator, or simply just called the FD estimator. So let's have a look at that. Let's go back to our panel data regression model. As before, we have our dependent variable y as a function of x. And on top of that, on the right-hand side of the equation, we include a time dummy, and then we have these two components of the combined error term. So we have AI, the unobserved individual specific effect, and then the idiosyncratic error U. Now this model holds for the pooled data. That is, we have data from period 1, data from period 2, we put them together, and then with that combined data, we can estimate the coefficients in this model. Of course, if the regressor, X, is correlated with AI, we know that OLS will be biased and inconsistent. So the question is, how can we go about that problem? Now what we can do is simply to write out the model for period 2. That is, now on the left-hand side of the equation, we have the dependent variable y in period 2 as denoted by the second subscript that's equal to 2. Because of the time dummy, the intercept on the right-hand side is equal to beta naught plus delta naught. And then we have our regressor, which now is indicated by 2 because we have observations from period 2, and in front of xi2 we have our slope coefficient beta 1, which we're interested in. Now, if we were to estimate this model just using data points from the second period, we would still have the same problem, namely that x is correlated with AI, so OLS will be inconsistent in this case as well. But this is the model as it looks for the second period. Similarly, for period 1, we have the following equation. So on the left-hand side, the dependent variable y is here indicated by subscript 1, meaning that we have observations from the first period, and then on the right-hand side, we have basically the same as above, with the exception that here the intercept is just equal to beta naught. And as before, we could estimate this model by OLS, but we would still have this problem of endogeneity, namely that x is correlated with the unobserved individual specific effect, AI. So the question is, how can we circumvent this endogeneity issue? And once you start looking at those two equations, well, you realize that alpha I is the cause of all evil. So the endogeneity problem is driven by this unobserved individual specific effect, according to the assumptions that we made up until now. So can we somehow get rid of AI? Absolutely. And the solution is basically just to subtract the first equation from the second. Or in other words, we compute first differences. So when we subtract y1 from y2, what we get is that the intercept in the first difference equation is equal to delta naught. Or put differently, beta naught cancels out. Besides that, we obtain the slope coefficient beta 1 multiplied onto the difference between x, our regressor in the second period, minus the regressor in the first period. And then in the end, we have the difference between the idiosyncratic error in period 2 and that error in period 1. And note right away that here, alpha I no longer enters the model. It's been differenced away. So what we end up with in the end is the difference in y as a function of the difference in x. That is the first difference equation. And in this equation, we still have an error term. And the error term is just the first difference between the idiosyncratic error in the two time periods. So if we think that the endogeneity issue is caused by AI, the unobserved heterogeneity, the good news is that it's been differenced away. And what we're left with is now a cross-section of first differences. That is, we go from 2 times n observations to only n observations after computing all the first differences. Now, with the first difference data, the key is we can estimate beta 1 consistently if we're willing to assume that the difference in the idiosyncratic errors are mean independent of x. Or put differently, that the differences in the idiosyncratic errors are uncorrelated with the differences in x. If that is the case, we can estimate beta 1 consistently using OLS or applying OLS to the first difference equation. Okay, let's have a look at an example. Let's go back to this example of returns to education. In this case, our dependent variable is equal to hourly wages, And we are interested in understanding how hourly wages depend on various characteristics. In this model, we have three explanatory variables. The first one is the local unemployment rate in a given worker's area in a certain time period. And the second explanatory variable is just the labor market experience for that particular worker in a given time period. And then finally, the variable of interest, xit3, equals the years of education that a given worker has obtained in, again, a given period. And then we have a panel data model. So our error term consists of this unobserved individual specific effect, AI, which we here think of as something like unobserved ability. That is something that's time invariant but unobserved. And then finally, we have our standard idiosyncratic error term. If we write this model in first differences, this is what we get. That is, the first difference in wages is a function of the differences in unemployment rates, differences in experience, and differences in years of education. And again, we see that we've differenced away this unobserved individual specific effect that we think is driving a correlation between the combined error term and education. Let me ask you a couple of questions regarding this example. So imagine you have panel data on wages, education, and experience for what we may call prime age male workers. In the data, education varies across workers, but it does not vary across time for any one worker. In other words, education is time invariant. The question is, can we estimate the returns to education using the first difference estimator? Answer A, no. Education is differenced out together with the unobserved heterogeneity, AI. B, yes, if a relevant and exogenous instrument, C, is available. C, yes, but it will be estimated very imprecisely. So again, please pause the video here and go to Epsilon and submit your answer. Thank you for your answer. Let's move on to a related question. So imagine having access to another sample of workers in two different time periods. In this new sample, you're told that 5% of the workers obtain a new diploma between the two time periods. As a result, education is not time invariant for this particular data. The question is, can we estimate the returns to education using the first difference estimator? A, no. Education is differenced out together with the unobserved heterogeneity, AI. B, yes, if a relevant and exogenous instrument, C, is available. C, yes, but it will be estimated very imprecisely. Now please pause here, go to Epsilon, and submit your answer. Thank you. Okay, what are the pros and cons of panel data? Well, as we've just seen, panel data allows us to eliminate unobserved time-invariant heterogeneity that may otherwise bias OLS if we just used purely cross-sectional data. Or in other words, we know that when we work with cross-sectional data, that firms, individuals, or countries are just very different both in observable ways and unobservable ways. And the fact that we have panel data, meaning we observe the same units over time, that allows us to sort of circumvent this issue that unobserved time-invariant individual effects may bias our OLS estimates. So the first difference estimator is just one way to get around this problem. One downside of panel data is that it's usually very difficult to come by. For instance, imagine you have surveyed a bunch of households in Africa, and then you want to go back to the same household and interview them again. Well, that may be an almost impossible task. On a similar note, it may also just be very expensive to conduct these panel data studies. That is, you need to hire people to go to Africa again, locate the same people, You may be able to find them, but it's just very, very expensive. Another downside of the first difference estimator is that, again, as we just saw, we cannot estimate the parameters on time invariant variables. So if we're interested in obtaining an estimate for the returns to education, we're facing with this fundamental problem that education doesn't vary a lot among people that have left school. That is, if we work with data with people older than 30 or 35 years, education doesn't vary, or it varies very, very little for those individuals. So how do you know whether unobserved heterogeneity is important or not? Well, if you have access to panel data, you can always estimate the model by OLS and also first differences. And if it so happens that the estimated OLS coefficients are very different from the estimated first difference parameters, well, that tells you, or it should tell you, that unobserved heterogeneity is important, meaning that OLS must be biased, which drives the difference between the two sets of results. And in this case, you will, of course, or you should prefer the first difference estimator, because that will be consistent. On the other hand, if OLS and first differences lead to very similar results, you would reach the opposite conclusion. You would conclude that unobserved heterogeneity appears to be less important. And in that case, you would tend to prefer OLS simply due to efficiency. Remember that we know that OLS is asymptotically efficient. Let's look at a panel data regression model that's not completely standard, in the sense that now we allow for the possibility that parameters vary across time periods. So as before, we imagine having access to a panel data, meaning we have observations on the same individuals in 2 consecutive time periods. And here, I, as before, denotes individuals and T index time. Here's the model. Let's focus on the first line that gives you the model for the second period. So on the left-hand side of the equation, we have our dependent variable y subscript I2. That's the observations on the dependent variable in period 2. Then on the left-hand side of the equation, we have one regressor, xi2, meaning we have observations on our explanatory variable in period 2. Now, the second period model has delta naught and delta 1 as the unknown parameters. Besides that, we have our usual error structure for a simple panel data regression model. Now, the second equation gives you the model for the first period, and everything looks the same, except now we have beta naught and beta 1 as the unknown coefficients that we're interested in obtaining. For this model, we're going to assume that x is correlated with the unobserved heterogeneity. And what could this model be an example of? Well, you can think of this model in the context of returns to education. And here, all we're doing is just to allow the return to be different in different time periods. So 1 additional year of schooling will increase your hourly wages by delta 1 in the second period, ceteris paribus. And on the other hand, 1 additional year of schooling will increase your wages by beta 1 units in the first period. Now the question is, can we estimate this slightly more general model using first differences? And now we'll go through 3 multiple choice questions where you have to answer that. This is the first question. Consider the equations we had on the slide before. Now my question for you is, what is the first difference equation in this case? So you should get out a piece of paper and a pen and start calculating. You're given 3 answer options, and once you've done your calculations, you should pause the online lecture, go to Epsilon, and submit your answer. Thank you. Let's move on to the next question. Now imagine you have this model. where the difference of y is a function of x observed in period 2 and x observed in period 1. Now you're told that the explanatory variable is time invariant. Moreover, you're told that delta 1 is equal to beta 1. The question is, will the first difference estimator provide a consistent estimate of beta 1 in this scenario? A. Yes, beta 1 can be consistently estimated. B. No, beta 1 drops out. C. No, only delta 1 minus beta 1 can be consistently estimated. And as before, please pause the video here, go to Epsilon and submit your answer. Okay, let's move on to the last question. With the same model as before, you're now told that delta 1 is different from beta 1. The question is, will the first difference estimator provide consistent estimates of both delta 1 and beta 1 in this scenario? A. No, only beta 1 can be consistently estimated. B. No, only delta 1 can be consistently estimated. And finally, C. No, only delta 1 minus beta 1 can be consistently estimated. Now for the last time, go to Epsilon and submit your answer. Thank you. This is the end of today's lecture on panel data and first differences. Next time, we'll follow up on this online teaching experiment, and on Thursday, I will provide an overall conclusion and a summary of econometrics B, and the following week, we'll review the most recent exams. See you Thursday. Good night.